Okay, we have already found Lorentz equations that allow us to go from one reference frame to another reference frame. Lorentz equations allow us to change what are the coordinates x, y, z, t in one reference frame and transform that into what those coordinates will be as measured from a different reference frame, x prime, y prime, z prime, and t prime. So now two people measuring the same event, an explosion for example, in two different reference frames will agree thanks to Lorentz equation. But what about velocity? What will be the velocity of an object as measured from one reference frame and from a different reference frame? How will two observers in two different reference frames will agree on the velocity of an object as far as they know their relative velocity? Or in other words, how Galileo addition of velocities equation is going to be written now in special relativity. We found that that equation, the Galilean addition of velocities, was the key of the problem that people found at the end of the 19th century when they tried to apply that to electromagnetic radiation, to light. So now we need to find that equation. In order to find that equation, we will assume we have two different reference frame S with coordinates x, y, z, t, and reference frame S prime with coordinates x prime, y prime, z prime, and t prime. Reference frame prime is moving with respect to reference frame S and is moving on the x direction. So now in order to derive the relationship among velocities, we go to the definition of velocity. So what is the velocity of a particle moving in our reference frame? Well, that's just the derivative of the position with respect to time. That is dx over dt. Well, we want to find a relationship between dx dt and dx prime dt prime. Let's define the variables that we are going to use. V will be the velocity of the reference frame. And now to distinguish the velocity of the particle from the velocity of the reference frame, we will use u as the velocity of the particle. So u, which is dt dx, will be the velocity of the particle from the station, and u prime, which is dx prime over dt prime, is going to be the velocity of the particle from the train. So these are Lorentz transformation equations. X and t are the position and time from the station, and x prime t prime are the position and time from the train. In order to find dx prime over dt prime, what we do is a differential of the position dx prime, and then we calculate the differential of time dt prime, and we use Lorentz equation to calculate that. In this case, dx prime is gamma dx prime minus v dt prime, and dt prime is gamma dt minus v over c squared dx. From here, we just divide dx prime over dt prime. On the left-hand side, that will be velocity from the train, and on the other hand, we have this a little bit more complicated expression, but we can cancel the gammas, and we get this other expression here. This, if we divide everything by dt, then what we get is that on the right-hand side we get dx over dt, which is just u minus the velocity of the train, divided by 1 minus v over c squared, and then again dx over dt, which is u. So we write this, and that's the transformation of velocities. But let's write it properly. And by properly I mean that we have just calculated what is the velocity of the particle on the x-axis, just the x component. So that will be u prime sub x is equal to u sub x minus v divided by this other term 1 minus u sub x v divided by z squared. So that's the transformation equation of the velocity that the particle has as seen from both reference frames. So again, u prime x is the velocity of the particle measured from the train. Remember, the prime will be for the train. The on prime is the velocity from the station, and v is going to be the velocity of the train, the relative velocity between both reference frames. Okay, let's just study a little bit this result. Let's assume that we have very small velocities compared to the speed of light. If we have that situation, then ux times v divided by c squared is going to be really small, much smaller than 1. So we can approximate that as the sum of velocities that we had in the case of classical mechanics. That's the Galileo transformation for velocities, which makes sense. Every time that in special relativity we impose that velocities are going to be small, then we have to recover Galileo. Let's go to the other extreme. Let's try to think what happens if both velocities are very high, near c. Let's assume that the train is moving to the right almost at c, and the particle is moving to the left almost at c. Galileo would say that the velocity of the particle as seen from the train is going to be 2 times c. But what does relativity say? Well, we have that, well, u sub x is c, v is minus c, so we get c plus c in the numerator, and we have 1 plus c squared over c squared in the denominator. This is just 2c over 2, which is c. So we cannot go faster than the speed of light. That's something we expected. We knew that, but we see that this transformation equation is robust enough and gives the result. And we could say that c plus c is c in special relativity. But all that we have just deduced is the change of the x component of the velocity from one reference frame to the other reference frame. But the particle could have any arbitrary velocity, vx, vy, and vz. Remember, the reference frame is always moving in the x-axis just for simplicity, but we could be observing a particle which is moving in x, y, and z. So now we know how the velocity component in the x direction transforms. Now let's find how the y and z components transform. But remember, it's the uy and the uz that we are interested in. So again, we go back to Lorentz equation. We're going to do the dy and dy prime. We will divide by dt prime, and we'll see what we find. These again are the Lorentz transformation equations, and now we write the y prime equal to y and z prime equal to z, and we do dy prime over dt prime, and using Lorentz transformations we get this ratio here on the right hand side. We have the non-prime coordinates on the right hand side, and we again do the same trick. We divide numerator and denominator by d1 over dt, and then every time that we have dt over dt, that is going to be 1. One time that we have dy over dt, that is going to be u sub y. So that's the transformation equation for the y component of a particle that we are observing from the train and from the station. And look, that the expression is different. This uy prime is different from ux prime, but it's the same for the c components. They are equivalent. Y and z are equivalent in this case, but the transformation equation is different, and we see that even though y is equal to y prime, uy is not equal to uy prime in this case. Look at this particularity. So the velocity in the x direction in one reference frame depends on the velocity in the x direction in the other reference frame, but the velocity in the y and z directions also depend on the velocity of the particle in the x directions. So look at u sub y prime, which depends on u sub y, but it also depends on u sub x and the velocity of the reference frame. So this is a little bit more nonlinear, a little bit more complicated expression on how to transform velocities of a particle moving in x, y, z direction from one reference frame or in another reference frame. Now let's do a simple exercise applying this relationship that we have just derived. Spaceship A moves away from Jakku at a velocity of minus 0.50 c, while spaceship B at the velocity of 0.7 c is again also moving away from Jakku. A. How fast is B's velocity in A's reference frame? And B. How does it change when the components uyb and uzb are added? Okay, here we have to be careful with the names of the velocities. So we have that A is minus 0.5c and uxb is plus 0.7c. This is the equation of transformation of velocities that we just derived. Now we have to see how we relate uxa and uxb to u sub x and v. So because v is the velocity of the reference frame, and now we are going to go to the spaceship A, which is that the moving reference frame, then the velocity of A is going to be the velocity of the reference frame, so v. And then the particle that we are observing is the spaceship V. So u sub x is going to be uxb, which is the velocity of the spaceship B, 0.7c. So we start using the equation of transformation of the velocities. That's the general expression that we found. Now we will rewrite that in terms of what we just found. That gives us a velocity of 1.2c over 1.35, which is just 0.89c. So that's the speed of the spaceship B as seen from spaceship A. Now we have to calculate the y and z component of the spaceship, assuming that that spaceship has a y and z component with respect to Jakku. There is not going to be any change in the x component of the velocity because u sub x prime only depends on u sub x and the relative velocity of the reference frame, but the y and z components do depend on the y and z component from the other reference frame. So what we have here is that this is u sub y prime in terms of u sub y and u sub x. Remember that y and z components do depend on the x component. And we have to calculate first gamma. Be careful here because gamma, which is 1 over square root of 1 minus beta squared, this beta is the velocity of the reference frame, v. So that beta is v divided by c. So which in our case it is 0.5 because that's the velocity of the reference frame with respect to Jakku. Then we get a gamma value of 1.15. Then the other term on the denominator, 1 minus u sub x v divided by c squared, we put the numbers, we have that. Now we have that u sub x is 0.7 and v is minus 0.5. From here we get that parenthesis is 1.35. With that in hand, then now we can go and calculate those velocities. First, what is the y and z component of the spaceship B as seen from Jakku? Well, it is minus 0.2c and plus 0.3c. So with that in hand, we substitute that in our equation and we obtain that the velocity prime in the y direction is 0.13c, and if we go to the z component again, we get that the final velocity in the z direction is 0.19c.